We will learn about the definition of continuity and how to apply that to solve a variety of problems. We say that a function f of x is continuous at x equals c, where c is some x value that we're choosing, if the limit as x approaches c of f of x is equal to f of c. So this first statement right here is our definition of continuity, but this statement is jam-packed with a lot of things that this means to have this equality sign. So let's really unpack what does that definition mean. So for a function f of x to be continuous at a point x equals c, we really need three things to happen in order to just have that equality statement from above. The first thing is that this limit as x approaches c of f of x has to exist. And by definition of a limit existing, we know that that must mean that the limit from the left equals the limit from the right. And we'll have to show this. So in our first step, the first thing we really have to show, especially with a piecewise function, is that the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. The second thing we need here, which is also key, is that f of c has to be defined. So what that means is there a place where if I take the value c, can I plug that into the piecewise function and get a valid output? From a graph perspective, it means really, is there a filled-in circle where x equals c and that value is defined for that coordinate pair? Now the third statement down here really just means that our first statement equals our second statement. So the limit as x approaches c of f of x that we found in part 1 by computing the left limit and the right limit equals the value for f of c that we found in part 2. From a graph perspective, what this means, let's draw it out. So the first statement, if we're assuming that the limit as x approaches c of f of x exists, then what that means is that no matter where I'm approaching from the left or the right, so let's say the graph does something like this and then maybe curves and goes down from there. I'm not sure what really the graph is doing outside of this. All I care about is in a neighborhood around x equals c. So what I'm looking at here is from both the left side and the right side on this graph, this limit exists and is equal to this value up here. Let's pretend it's the number 5, just for this example. So as I approach in from the left and from the right, I can see that both of those limits are approaching a y value of 5. That's what the first statement means. The second statement means that there is a filled-in circle for f of c. Now it doesn't mean it has to be at 5 in the second statement, but there should be some filled-in circle. What the third statement tells me is that that filled-in circle should be exactly where the limit is approaching. So in this case at 5, since the left and the right were both equal to 5. And this would give us a function that is continuous. Now if any of the three prior statements fails, then the function is automatically considered discontinuous at x equals c, and we say that c is a point of discontinuity. And later on we're going to talk about really what are the different types of discontinuities, because there are different types, and we'll see examples as we kind of go and draw the graphs with these. The key thing I really want to point out though is not just that I need these three things to be true, but when we're talking about continuity, we're just talking about continuity at one x value at a time. So just because a function might be continuous at, let's say, x equals 2, that does not mean it's necessarily continuous everywhere else. So if I were to prove that a function is continuous everywhere, it would require that I'm proving it for every single x value on that domain then. Let's look at our first example. So our first example says determine if f of x is continuous at the given value of x, justify your answer. So for all of these, we're going to be looking at piecewise functions. So as a little refresher, a piecewise function is a function that's defined in multiple pieces or multiple parts. So in this first example, we have f of x equaling x minus 2 over x squared minus 4 if x is strictly less than 2, and 1 over the square root of 4x squared if x is greater than or equal to 2. So what this means is that if I'm looking at any x value that is less than 2, so 1, 0, any negative numbers, or even all the way up to 1.99999 repeating, we're going to be using this top function, which is x minus 2 over x squared minus 4. Now if we're looking at any x values that are greater than or equal to 2, so starting with 2 and taking any number bigger than it, we'll be looking at the function 1 over the square root of 4x squared. and they want to know in this example, is f of x continuous at x equals 2? So x equals 2 is considered the break point of this piecewise function because it's where it could potentially break from one part of the graph to another, and really the question we're asking is, do these two graphs meet up together and the function value equal there, because then I would have a continuous graph at x equals 2. So the first thing we've got to check is, does the limit even exist? Because if the limit doesn't exist, there's no way for a function to be continuous. So to see if a limit exists, I have to compute the limit as I approach from the left and the right hand side. So I'm going to start with the limit as x approaches 2 from the left side. Oops, sorry, that's a little messy. Of f of x. So as you can see, I left this very general. I just left it as f of x, and I really need to determine, well, I've got two parts to this function f of x. Which one am I using as x approaches 2 from the left-hand side? Well, if I go back to a graph and I think about the left-hand side, we're looking at values that are smaller than it then. So I want to take the top piece of it because it's where x is less than 2, and if I'm less than a value, I am to the left of it. So for us, that means we're really looking at the limit as x approaches 2 from the left-hand side of x minus 2 all over x squared minus 4 then. Now if I try to do a direct substitution into this, I'm going to get 0 on top, which could potentially be fine, but in the denominator I'm also going to get 0, which means I have an indeterminate form of 0 over 0, so hopefully there's some way that I can algebraically manipulate this right now. So one thing I notice is I can factor the denominator. So x squared minus 4 can factor as x minus 2 times x plus 2. So I'm going to go ahead and rewrite this in factored form. Limit as x approaches 2 from the left. So I still haven't taken my limit, so I have to make sure I'm writing that limit. In the numerator, I'm not changing anything. It's still x minus 2, but in the denominator, I can go ahead and factor this as x minus 2 times x plus 2. From here, I can see that now that I'm in factored form, I can cancel the x minus 2 over the x minus 2, and this is going to be equivalent to the limit as x approaches 2 from the left of 1 over x plus 2. Because technically, although I canceled the x minus 2, there's still a 1 in the numerator left over. From here, I can now do a direct sub in, and I would get 1 over 2 plus 2, so that would be equal to 1/4 then. Notice I stopped writing the limit since I have now evaluated the limit by subbing in directly what x is approaching. So what we found so far is that the limit as x approaches 2 from the left of our function is going to be equal to 1/4. The next thing I need to check is, well, what's happening as I approach from the right-hand side? So if I take the limit as x approaches 2 from the right-hand side of f of x, I have to think about what function do I get to use this time if I'm approaching from the right-hand side. So I'll still have my limit, so I'm going to go ahead and just rewrite that so I'm ready to go. And if I'm to the right of 2, if I think about a graph and I'm to the right of an x value, I'm looking at numbers that are bigger than it. So I want to use the bottom function here since that's the piece where x is greater than or equal to 2. It doesn't matter right now where the equals to sign is when I'm taking a limit. I'm just comparing if I'm to the right of it, I want values that are greater than, and if I was to the left, that's why we use the values that were less than it. So I'm going to take the limit as x approaches 2 from the right of 1 over the square root of 4 times x squared. Now if I do a direct substitution in right away, I'm able to because I don't end up getting 0 in my denominator. So I get 1 over the square root of 4 times 2 squared by directly subbing in. Now from here I can simplify that further, and this is really equal to 1 over the square root of 16, and then we know that the square root of 16 is equal to 4. So I also got 1/4 for the limit as x approaches 2 from the right-hand side of f of x. What this tells me is that the limit as x approaches 2 overall, so the overall limit of f of x is going to be equal to 1/4 then. I don't know yet if this function is continuous or not. All I have proven so far is because the limit from the left equaled the limit from the right, then the overall limit there, so the limit as x approaches 2 of f of x is then equal to 1/4. That is not enough to say that the function is continuous yet. In terms of a graph, all that I have shown, so if I go to graph this so we can see a visual behind this, while I'm approaching 2, all that I know is that, let's label this as 1/4 on the y-axis, is that when I approach from the left-hand side, it was approaching 1/4, then from the right-hand side, it was also approaching 1/4. So right now, this is all that I know, and that is not enough to prove that a function is continuous because I don't know if the filled-in circle gets to go there as well. So that's where step 2 comes into play. I need to find f of c, or in this case, I need to find f of 2. To figure out which part of the piecewise function I get to use at 2, that's where I start paying attention to where is the equal sign, or is there even an equal sign, because there doesn't have to be in all of these cases. So in this example, the equals to sign is with the bottom function because it says x is greater than or equal to 2. So what that means is when x equals 2, I want to use this bottom function here being 1 over the square root of 4 times x squared. Now be careful here. I wouldn't want to write equals 1 over the square root of 4 times x squared because that's not actually true. This is what f of x is equal to. We're looking for f of 2. This is what we call a syntax error because technically f of 2 does not equal 1 over the square root of 4 times x squared. Instead, remember from function notation that if I'm finding f of 2, that means I'm plugging 2 in for the x's. So to fix this, I need to not have 1 over the square root of 4 times x squared, but 1 over the square root of 4 times 2 squared. And I want to make sure I have done that substitution since I have my numeric value already in for f for x in this case. Now if I simplify that down, I know that that's going to become 1 over the square root of 16, which is equal to 1/4 then. So this piece right here that we first found at the top with the limits, that's really the step 1 that we were finding, of finding does the limit exist. And then this second piece is our step 2 of determining what is the function value, or does the function value actually exist. And then step 3 really says, are those equal? Well, in this case, the limit as x approaches 2 f of x was equal to 1/4, and f of 2 is also equal to 1/4. So yes, this function will be continuous then, and we're going to want to write out all of that explanation that we just talked about. So since the limit as x approaches 2 of f of x is equal to 1/4, which is equal to f of 2. Oh, let's make that a little bit nicer, cleaner. There we go. That's easier to read. So since the limit as x approaches 2 of f of x, which equaled 1/4, also equals f of 2, then yes, f of x is continuous at x equals 2. And it might seem a little silly to have to write all of that out, but our job is to justify our answer. That was part of our original question up here. It did say to justify your answer, and so that means I have to completely explain my thought process then. Yes, I know that I'm going through all of this proper notation of showing the limit is equal to 1/4 and then showing the function value and making sure all of this is using correct notation, but I have to then explain what that really means. So an AP grader isn't going to take that at face value. It's your job to explain that in your problem. From a graph perspective, what this means is we already knew from step 1 that the limit from the left and the limit from the right were equal to each other, and we're both approaching 1/4. What step 2 told us is that I have the coordinate pair then, so this is, remember, relating back to that coordinate pair 2, 1/4. being on my graph then, so I know that I also get this filled in circle right here where both the limit from the left and the limit from the right are approaching. This then is for sure going to be continuous at x equals 2, since the limit from the left equals the limit from the right also equals the function value then. Let's look at another example. So in example 2, we have another piecewise function. It's defined a little differently, and we'll talk about it, but it says f of x equals x squared minus 1 over x minus 1 anywhere where x does not equal 1. And then f of x equals negative 1 when x equals 1. So this is different than our prior example because we don't have any inequality symbols here. Instead, what's happening is that f of x is going to take on this top function, so this x squared minus 1 over x minus 1 everywhere except at 1. So no matter where you are on this graph, you're going to use x squared minus 1 over x minus 1 everywhere except at 1. And then when x equals 1, I'm at the value of negative 1. What this means when I go to compute all these steps, remember our first job is to see, does the limit exist, meaning the limit from the left, does that equal the limit from the right? Well, I'm going to use the top function here for both the limit from the left and the limit from the right, since it's taking on both the bigger than values and the smaller than 1 values. So what that means is I could go through and separately compute the limit from the left and the right, but I actually don't need to since I'm using the same function for both of those. So I'm going to go straight to computing the overall limit, so the limit as x approaches 1 of f of x. For both the left and the right, because they're using the same function, I can go ahead and combine these together right off the bat. Now, if you're not convinced by that, you can go ahead and compute the limit separately, and you will see that you end up using this x squared minus 1 over x minus 1 for both the left and the right limit. Now, if I try to do a direct substitution into here, I'll end up dividing by 0, and I'll have a 0 on top, so I have that indeterminate form of 0 over 0 again. So hopefully there's some way that I can algebraically manipulate this to find the limit. What I notice again is that I can go ahead and factor this guy. So I can factor the numerator, so I'll have the limit as x approaches 1 of x minus 1 times x plus 1 by factoring that numerator there, all over. Now in the denominator, I can't factor it, so I'm just going to rewrite the x minus 1. Conveniently, the x minus 1s can cancel again, and I'm truly looking at the limit. The limit as x approaches 1 of x plus 1. And what that's going to be equal to, I can do a direct substitution, and I get that that's equal to the value of 2. So step 1, I'm good. I showed that the limit exists, that both the left and the right were using the same function, so this limit is going to be equal to 2. But again, that's not enough to show continuity. And I want to keep going back to the graph so that we have a visual to go with this. So what this is meaning is that as x approaches 1, from both the left and the right side, we're approaching this value of 2. And I keep drawing an open circle because we have not figured out what's going on at x equals 1. So all I know is that from the left and from the right, they're both meeting up, but we don't know what's happening exactly at 1. That's where our step 2 comes into play. That's where I want to figure out, well, then what is f of 1 going to be equal to? And to figure out what f of 1 has to be equal to, if I go back to the piecewise function, I have to use the part of the piecewise function that deals with where x equals 1. So in this case, I'm going to use the bottom function because that's where x is equal to 1. So f of 1 then is going to be equal to negative 1. Now there's no place to plug the 1 into because f of x is already defined to be a constant. Now, hopefully what we've noticed now is that the limit was equal to 2, but the function value is equal to negative 1. So if I go back to the graph and I draw it, realizing, let me erase that so I have space, is that when x equals 1, I have the closed circle down here at the negative 1 value. And in this case, although the limit exists, it does not equal the function value, since the function value is down here at negative 1 and the limit was up there at 2. So in this case, this function is going to be discontinuous because that limit does not equal the function value. And so to explain that, we would say since the limit since the limit as x approaches 1 of f of x equaled, in this case, 2, there we go, which does not equal, since 2 does not equal -1, and that was equal to f of 1, then this function f of x is discontinuous at x equals 1. So then we say that f of x is discontinuous at x equals 1. And hopefully the graph's another reminder of that visual there, that although the left and the right limits are equal, it doesn't equal the closed filled-in circle. So if we're thinking about this from like an algebra perspective, well, I can't draw this graph without picking up my pencil, so then the function would not be continuous then, since there, in this case, is a hole in the graph. Let's look at our third example. I'm going to go ahead and have you guys try your third example on your own first. So pause the video right now and try this, and then we'll check 3 together. Okay, as we check 3, I have this piecewise function that says f of x equals the absolute value of x plus 2 when x is less than or equal to 1, and f of x is equal to x minus 2 squared when x is greater than 1, and we're curious about the continuity when x equals 1. So the first thing we have to check is the limit from the left and the limit from the right and see if those guys are equal. So let's start with the limit from the left. So if I take the limit as x approaches 1 from the left of f of x. Now for the left side, I want to use the stuff that is less than that. So I'm going to use the absolute value of x plus 2 in this case, since that's where x is less than 1. So don't forget to keep writing your limit until you take it. So we have the limit as x approaches 1 from the left of the absolute value of x plus 2. If I try to do a direct sub in, I get the absolute value of 3, which is a valid answer, and the absolute value of 3 is equal to 3. So I'm good on that front. The next limit I've got to compute is the limit as x approaches 1 from the right-hand side of f of x. Now if I approach 1 from the right-hand side of f of x, that means I'm looking at values that are bigger than 1, so I'm going to use the bottom function in this case, which is the x minus 2 squared piece. Now if I do a direct sub in again, that will work as well, and I end up with 1 minus 2 whole thing squared, so I end up with -1 squared, which would be equal to +1. Well, in this case, here's an example that we haven't seen like this before. Our limit as x approaches 1 from the left of f of x was equal to 3, so if I go to a graph and I draw this, as x approaches 1 from the left, I'm up here at 3, not really sure what it's doing to the left, I'll just draw that squiggle line. But then as I approached 1 from the right-hand side, I was down here at 1, so let's pretend it does something like this. Well, because the limit from the left here doesn't equal the limit from the right, then we know that the overall limit doesn't exist, which will then in turn tell us that this function is discontinuous. So if we're going to write that all out formally, we would say since the limit as x approaches 1 from the left-hand side of f of x does not equal the limit as x approaches 1 from the right-hand side of f of x. Since one of those values was 3 and one of those values was 1, so those guys are not equal, then that tells us that the limit as x approaches 1 of f of x, so the overall limit, does not exist, or DNE for short, since the left-hand side doesn't equal the right-hand side. So then this automatically tells us that f of x then is discontinuous at x equals 1 then. So in this example, the only thing we ended up really computing was that first step of seeing if the limit exists. But because that limit failed to exist, then we automatically can say that f of x is discontinuous. There's no need to go through trying to find the function value, because even if the function value is at one of these 2 points, it still will not make the function continuous, since there is this like break in the graph that we have going on, because the left limit did not equal the right hand limit. So that's one of those kind of nicer examples that we have, because if that first step fails of the left limit not equaling the right limit, then I can automatically say that the function is discontinuous. On the flip side of that, though, we've seen, though, that just because in our prior example the limit did exist, so the limit from the left equaled the limit from the right in example 2, and they were both equal to the value of 2 in this case, that wasn't enough to prove that the function was continuous. We'd take it a step further and compute the function value, but in this case, since the function value didn't equal the limit in our second example, that's why the function was discontinuous. So although examples 2 and 3 are both showing that a function is discontinuous, they're really 2 different cases for why the function is discontinuous. And we're going to talk about those different types of discontinuities as we get further into this video. We can even see from the graph right now that in example 2, yes, they both met up on the same side and there was a hole there and the function value was somewhere else, versus on example 3, the left and the right do not meet up and there's this like break or this jump in the graph that we're seeing. Okay, let's look at example 4. Again, I'm going to have you guys go ahead and pause the video and try example 4 on your own first to see what you get, and then we'll check it all together. Okay, let's check example 4. So I'm going to guess that one of the first things you guys did was compute the limit as x approaches 5 from the left and the limit as x approaches 5 from the right, because that was our step 1. So it's what we've been doing every time. Then you probably looked at, well, let's find f of 5. Well, in this case, if I look at this piecewise function, there's something that's very different about this one compared to any of our prior 3 examples. Let's go ahead and read it. So it says f of x equals 5x plus 2 when x is greater than 5, or when x is less than 5. And then for the bottom case, it says f of x equals x squared plus 2 when x is greater than 5. Well, the first thing I'm noticing is, where is the equals to bar? Which function do I get to use when x equals 5? Well, I don't know. I can't use the top function because strictly x is less than 5, and I can't use the bottom function because that's where x is bigger than 5. So this is very different because I have no equals to sign. And that's going to be a big problem because we're talking about what's happening with the continuity at x equals 5, but there's no place where x gets to equal 5. So right off the bat, although it's perfectly correct if you guys went ahead and did the limit from the left and the limit from the right, the first thing I'm going to state is that f of 5 is undefined, because there's no place where I have an equals to sign to be able to show me which function to use, which means if I try to compute f of 5, there is no value for it. So we call that undefined then. So right off the bat then, it doesn't matter what the limit from the left and the limit from the right are. If f of 5 is undefined, then f of x is discontinuous. So I can say right away then f of x is discontinuous. Such a long word to write out. I'm sorry, the pen tablet is having some issues today. particularly f of x is discontinuous, I should say at x equals 5. It's actually continuous everywhere else, but specifically we're talking about at x equals 5. And on a graph, what I think about is no matter if I compute the limit from the left or the right, for the sake of space, I don't really have space to do that anymore, but you could. I do think they're going to both be equal to each other. Yeah, they're both going to be equal to each other, but what I notice here is that there's no filled in circle at x equals 5. Which is automatically going to make this discontinuous. Now, if you computed the limit from the left and the limit from the right, you should have gotten 27 on both of those. So although I have this case here where I have the graphs both approaching something, the reason it's approaching 27 because if I do a direct sub in, I'll get 5 times 5 plus 2 for both of them. So 25 plus 2 will give me 27. But they're approaching a open circle, and then there's no other place with a filled in circle when x equals 5. So I get a graph that looks like this then. Okay, our fifth and final example where we're trying to either prove continuity or disprove continuity. And again, why don't you guys go ahead and pause the video and try this one on your own first. Okay, example 5, let's check it. It says f of x equals cosine of pi x if x is greater than 1, and then it says f of x equals sine of 3 pi x over 2 if x is less than or equal to 1. Well, you probably were looking for the equals to sign after the last example there, so we do have an equals to sign, so there is a chance that this is going to be continuous at x equals 1, so let's go ahead and compute all of these. I'm going to go back and start with the limit from the left. So as we find the limit as x approaches 1 from the left-hand side of f of x, which function will I be using then as we approach 1 from the left-hand side? So as I approach 1 from the left-hand side, I want the values that are less than, so we're going to be dealing with the bottom function in this case, the sine of 3 pi, well that was a messy 3. A little bit better, 3 pi x over 2. I can do a direct substitution in for this one, so I'll get sine of, well if I sub in 1, I just get 3 pi over 2 since the 1's not going to change anything. And then sine of 3 pi over 2, we can't forget about our trigonometry, sine of 3 pi over 2 is going to be equal to -1. A little refresher up here, if I draw my unit circle, 3 pi over 2 is down here on the negative y-axis, and we are looking at the coordinate pair 0, -1, and sine deals with the y values, so I get -1 then. Let's do the same thing for the limit as x approaches 1 from the right-hand side of f of x. Now in this case, as we approach from the right-hand side, I'm going to use the top function since we're looking for the places where x is bigger than 1, so we'll be using the cosine of pi x. I can do a direct substitution in for this, and I get cosine of just pi then, which, remembering our trigonometry, cosine of pi is also equal to -1. And if I refresh around the unit circle, pi is over here on the negative x-axis, which is the coordinate pair -1, 0, and we know cosine deals with the x values. So in this case, both the limit as x approaches 1 from the left-hand side of f of x equals the limit as x approaches 1 from the right-hand side of f of x. So what that tells me then is that the overall limit, so the limit as x approaches 1 of f of x is going to be equal to -1 then as well, since the left equaled the right limit in this case. Now again, this is not enough to prove continuity. If we go to a graph and we were to draw this, all that I know is that as I approach in from the left, something's happening. I'll make it like a sine wave this time. As I leave from the right. They're both approaching the same value, but I don't know about that filled in circle yet. So my next step is to compute, well, what is f of 1? So as I go to find f of 1, which function will you be using in this case? So at x equals 1, I'm looking for the one that has the equals to bar. So in this case, I'll use the bottom function. Remember, I want to make sure that I'm plugging in the 1 right away for the x, so I don't want to leave the x there. I want to plug in 1. So I'm looking at sine of 3 pi times 1, which I don't really need to write. So 3 pi over 2 then, or 3 pi times 1 all over 2. Now we've already computed sine of 3 pi over 2. That is equal to -1. So in this case, our filled in circle happens to be where the left and the right hand limits are equal to, so that tells me that this function is going to be continuous. And we'll go ahead and write out the formal justification for y. So since the limit as x approaches 1 of f of x is equal to f of 1, then yes, f of x is continuous at x equals 1. Awesome. Couple of things about notation I want to point out before we move on from this example, just to make sure you guys are noticing and are aware of them. So in terms of limits, in each one of these steps, I have written what limit I have. So let me I'm going to use a smaller highlighter. So in each one of these, I still have a limit written until I actually sub in for the limit. So you'll notice in my third step here, there's no limit in front of the sine of 3 pi over 2 because I've subbed in for that limit. So that's why there's no more limit here. Just like as I did the limit from the right, I have it in the first two steps because I haven't taken the limit yet. But then in this third step, there is no limit here and there shouldn't be. So I'm good here. There shouldn't be a limit since I've done a direct substitution in. Then the other thing I want to bring up is that syntax error kind of thing that we talked about earlier with making sure if I'm finding f of a number that I plug that number in. So as we could see, I had no x here. Although it's 3 pi x over 2, I had already subbed in the 1 for x, so I wouldn't write it. Let's go ahead and talk about these types of discontinuities. So we've seen different examples here from the prior 5 examples that we had. And each one of them has represented a type of discontinuity, and we have 3 types of discontinuities that we are going to talk about. So the first type is what we call removable discontinuity. So this happens when the limit as x approaches c of f of x exists. So what that means, the left-hand limit equals the right-hand limit, but either f of c is undefined or that function value exists but just isn't equal to the limit. So let's go ahead and draw a graph for both of these so that we can see what they're looking like. So I'm going to do the first case where f of c is undefined in purple on the left-hand side here. So on both of these graphs, as I'm going to draw the kind of 2 different types of examples here, we know that the limit as x approaches c of f of x exists. So that means the left limit and the right-hand limit meet up together. But in this first example, f of c is undefined then. So I mean, I have no filled in circle then, where x equals c. Now in the second case over here, I'm going to go ahead and draw it in blue on the right. What it says is that the limit still exists, so I still have the left limit equaling the right limit. So they both meet up from either side, but then the function value is just somewhere else. So why don't I draw the function value up here then? Both of these cases are called removable discontinuities because the function value has been removed out from the graph that the left and the right hand side meet up from. And it doesn't matter if it's been removed and taken away completely or kind of removed and placed somewhere else. In Algebra 2, you might have heard the phrase that there is a hole in the graph. This is kind of that example where there is a hole in the graph. Although the left and the right-hand side meet up, there's that hole there because it was removed from the graph. In our second type of discontinuity, it's what we call a jump. This happens when the limit from the left does not equal the limit from the right. So that was kind of that first case that if it failed and the left equaled the right, I was automatically discontinuous. Now there's a bunch of examples we could draw with this one depending on where the function value is, but in this case the function value does not matter. So I'm going to write this up on the side just because I'm not going to draw all the different cases with the function value, but the function value, the f of c, does not matter. Ooh, that got really messy. So no matter what, the function value does not matter, just means that the left doesn't equal the right. So in one example, I'm going to have the left-hand limit be up here at some value. Let's say the right-hand limit is down here, and I'll just color in the bottom circle down here. But it really does not matter where that filled in circle is. So I'm also going to draw an example where maybe the left-hand limit, let's say, is still up here. The right-hand limit is down here, and maybe the filled in circle is way up here. There could also be a case where there's maybe no filled in circle at all, or maybe the filled in circle is with the limit from the left. It actually does not matter where that filled in circle is. All that matters here is that the limit from the left doesn't equal the limit from the right. So just to make sure we can write that out mathematically, if we were asked to justify a jump discontinuity, we would say that the limit as x approaches c from the left-hand side of f of x does not equal the limit as x approaches c from the right-hand side of f of x. Regardless of where f of c is, the left limit does not equal the right-hand limit, which automatically then tells me the limit as x approaches c of f of x does not exist. And although this last statement that I wrote of the overall limit not existing is true, really what's important here and the key thing is that the limit from the left does not equal the limit from the right. And we would use this if we were asked to formally justify a jump discontinuity. And hopefully from the graph you can kind of see a little bit why we call it a jump discontinuity, because there's this break or this jump in the graph. And if you're thinking about like playing a game, I have to jump from one piece to the other if I was going to keep moving along this function. The last type of discontinuity that we are going to talk about is called a discontinuity due to a vertical asymptote or an infinite discontinuity. And this happens if one or both of the one-sided limits does not exist or is infinite. So I'm going to go ahead and highlight that for us. So this happens if one or both of the one-sided limits do not exist or they are infinite. And we then say that f of x has a discontinuity due to a vertical asymptote. So I'm going to draw two examples just for us to see. So in this first example, let's say I have a vertical asymptote here, and maybe the left side of the graph is going down, and the right side of the graph is going up towards positive infinity. This is a infinite discontinuity because in this case, well, both sides are infinite, and that limit is then not going to exist since they're going either direction. And in another case, even if they both met up to, let's say, positive infinity, so in this second example, if I draw this and they're both going up towards positive infinity, that's fine. I still have a discontinuity here because one, or in this case, both one-sided limits are infinite. So if we were to justify this graph on the right, we could say the limit as x approaches c from the left-hand side of f of x equals infinity. That would be enough justification. You could also justify it by saying the limit as x approaches c from the right-hand side of f of x also equals infinity. But I really just need one of those to justify it, since one or both could be infinite limits. On this first graph that we had over here, if we were going to justify it using notation, we would say the limit as x approaches c from the left of f of x is equal to negative infinity. That would be enough to justify it, since that graph is going down towards negative infinity on the left-hand side. Or if you prefer to say, we could say the limit as x approaches c from the right-hand side of f of x equals positive infinity in this case, since that's going upwards. And from here we can kind of see through these three different examples, and hopefully from the graphs give you a nice visual of it. Really, these are all different types of discontinuities, from the removable, which happens because the limit exists, so the left side equals the right side, but the function value does not exist here. So writing this out with formal notation just to make sure you guys have it, here on our first example we'd say the limit as x approaches c. Oh, actually I can go right to saying that, oh no, I'll add both of them there. Limit as x approaches c of f of x exists but f of c is undefined. Oop. Just got a shorthand undefined there so I don't run out of space. And then on this graph on the right, we would say that the limit as x approaches c of f of x, yes, it does exist, but it does not equal f of c, since we knew what f of c was defined as. So it makes sense to have this not equals to kind of statement here, since we actually have a value for f of c. What I think would be a really good idea now is for you guys to pause the video, go back to those prior 5 examples, and for any that were discontinuous, determine what type of discontinuity they were now based off of what you have. Let's check that actually, just to make sure that we're all on the same page. So if I scroll back up to our first example was continuous, but our second example was discontinuous, and the type of discontinuity here that we have is removable. And the reason being behind that is this statement that we have right here, that I'm putting kind of a blue box around so that we can see it, which says that the limit as x approaches 1 of f of x does not equal the function value, or f of 1 there. So example 2 was a discontinuous example, and specifically it was a removable discontinuity. In example 3, it was also an example where the graph was discontinuous, and in this case it is a jump discontinuity. And that is because the limit as x approaches 1 from the left of f of x did not equal the limit as x approaches 1 from the right of f of x. And I've boxed that reasoning down here for us in blue. So if the question instead said, explain what type of discontinuity we had, we would say we have a jump discontinuity, and this stuff in the blue box that says the limit as x approaches 1 from the left-hand side of f of x does not equal the limit as x approaches 1 from the right-hand side of f of x. Example 4 was also a place where we have a discontinuity, and this is a removable discontinuity. And the reasoning behind this one, although I don't already have it pre-written out exactly, would be that the limit as x approaches 5 of f of x exists. Now we technically didn't show this, so we would want to actually show this, and that is an E. So the limit as x approaches 5 of f of x exists, which we would still need to show, but what we used earlier was that f of 5 is undefined. So we would say that piece, which makes it a removable discontinuity. And then in our fifth example, it was continuous, so no type of discontinuity to find there. Okay, moving on to our last couple types that we're going to talk about. So there are some functions that we are very used to using, and we can actually assume that they're continuous functions. So a continuous function is a function that is continuous at every point of its domain, which is key. We're not talking about things that are outside of its domain, but just on its domain. And we are allowed to use the fact that these functions are all continuous on their domain. So polynomial functions, so polynomials include a lot of things: linear functions, quadratics, cubics, fourth degree, fifth degree, and etc. All of those polynomial functions are continuous on their domain. So are nth root functions, rational functions on their domain, trig and inverse trig functions, exponentials, and logarithmic functions. We can assume that those are all continuous. So we'll see as we go on through kind of other concepts, if we have to have a function being continuous to apply something later on, which is a big part of calculus, if we have any of these 6 types of functions, we could automatically say that they are continuous functions without having to prove it. The next thing I want to talk about is, although there are functions that are discontinuous, sometimes those functions might be continuous from one side. So we have this concept called one-sided continuity at a point. And what it says is a function f of x is right continuous. So I could be right continuous or continuous from the right if the limit as x approaches c from the right-hand side of f of x equals f of c. What that's really saying is that if I approach in from the right-hand side and the filled-in circle is also there, then that function is then considered right continuous. On the flip side, we can have a function being left continuous, or continuous from the left at a point x equals c, if the limit as x approaches c from the left equals that function value then. So on a graph, if I were to come in from the left-hand side and there's a filled-in circle there, even if there's a jump in the graph, but if I have a filled-in circle there from the left, I am considered left continuous. Using this graph below, why don't you guys pause the video and decide if this graph is something that is right continuous or left continuous. Okay, let's check this. So in this graph, when I'm looking at it, as I come in from the left-hand side, I'm approaching the value of 1, and as I come in from the right-hand side, I'm approaching the value of -3. And if I notice, the filled-in circle here is up at 1, so in this case, we are considered left continuous. So this graph shows that f of x is left continuous, and we can justify why in a second. So I'm going to shorthand continuous with just C-O-N-T, but this is left continuous at, in this case, x equals 2, and the reason behind it would be that the limit as x approaches 2 from the left-hand side of f of x, which equals 1, also equals f of 2, or our function value at this point. This function is not right continuous, and the reason being here, or at x equals 2, let me be specific, and that reason is that the limit as x approaches 2 from the right-hand side of f of x equals -3, which does not equal the function value, which happened to be at 1. So from this graph, we do have a value that's left continuous since the limit from the left equals that filled-in circle, but it is not right continuous since that limit from the right is going towards an open circle. Okay. AP style questions. So we could put a twist on this. So in these examples, what we're going to use is we're going to be given the fact that f of x is continuous everywhere, and use that to kind of work backwards and figure out what the original function is going to be then. So these examples say, find the value of k. So k is going to be some constant, some numerical value, so that f of x is continuous everywhere. So we're now given that f of x is continuous, and our goal is to find the value of k where that would then be true. So we're working backwards. So instead of being given our function f of x and seeing if I have a continuous function, we're going to assume that f of x is continuous, and we want to kind of solve the puzzle on what would be this missing value k. So one thing that we definitely want to take advantage of is that definition of continuity. So as a reminder, why don't you guys list the 3 things that have to be true for a function to be continuous without looking at your notes. So pause the video right now and try to write down what those 3 things are. Okay, let's check them. Doesn't really matter the order. The first one that we talked about was that the limit had to exist, which really means that the limit as x approaches c from the left-hand side of f of x has to equal the limit as x approaches c from the right-hand side. So that's the first thing that has to be true. The second thing is that f of c exists and is defined. And then the last part of continuity says that the limit as x approaches c of f of x has to equal that function value f of c. The one we're going to focus in on for continuity is really going to be the first one in this case. So we get to assume that all 3 of these things are true, but what's really going to help us solve for this value of k is computing the left limit and the right-hand limit and then setting them equal to each other. So let's go ahead and start with that. So we're going to start by computing the limit as x approaches, in this case, 0, since 0 is our breakpoint. So the limit as x approaches 0 from the left-hand side of f of x. I know that that has to be equal to the limit as x approaches 0 from the right-hand side of f of x, since we get to assume that this function is continuous. So let's go ahead and find both of these. So if I'm computing in from the left-hand side, I want to think about which function do I get to use. So my original problem says f of x equals 3 if x is less than 0, and f of x equals x squared plus k if x is greater than 0. So as I approach in from the left-hand side, which function do I get to use? Well, as we come in from the left-hand side, I want to be less than that value, so I get to use the function 3. So then the limit as x approaches 0 from the right-hand side then is going to be the x squared plus k, since I want to use the function where x is bigger than 0. I can go ahead and do a direct sub for both of these limits. The limit of a constant is just that constant itself, so I get 3. If I do a direct substitution here, although it seems a little silly to write, I get 0 squared plus k. Remember, k is that constant I'm looking for, so I wouldn't plug 0 in for it, since that's the value that x is approaching, not what k is. Then from here, well, 0 squared is 0, so 3 equals k. And we were able to find that value for k that makes this function f of x continuous. Now, I do want to make the overarching statement that not everyone might work out just as nice as that one did. Sometimes there could be more algebra involved that we have to solve from this step right here after we've taken the limits, but even if I have more algebra involved, we can still do that and eventually solve for k. Okay, example 7. Why don't you guys try example 7 on your own first, and then we can check it. So example 7 says find the value of k so that f of x is continuous everywhere. And f of x is equal to x minus k if x is less than 2, and f of x is equal to x squared plus 2 if x is greater than or equal to 2. So same type of problem we had before. We get to assume now that f of x is continuous, so those 3 parts of that definition I get to use now, and I know that they're all equal, and I want to find the value of k. Again, I'm going to start with that limit from the left and the right hand side because that's going to give me an equation to work with, and by having that equation to work with, I can then start to piece together and find what k is. I'm going to take the limit from both the left and the right as I approach 2, since 2 is the break point of this piecewise function. So I'm going to take the limit as x approaches 2 from the left of f of x. Now, since f is continuous, that has to be equal to the limit as x approaches 2 from the right of f of x. And from here, I can sub in each one of those and try to figure out, well, which function am I using? So as I approach 2 from the left of f of x, would I be using the top function or the bottom function? In this case, we're going to be using the x minus k, since we're looking at the piece where x is less than 2. And that will have to be equal to the limit as x approaches 2 from the right-hand side. Well, that was a very messy 2, I'm sorry. As x approaches 2 from the right-hand side, so we're using the x squared plus 2 piece from here. I can go ahead and sub in for these limits. So as x approaches 2 from the left, I'll get 2 minus k, since a direct sub will work. And then as we approach 2 from the right, I can also direct sub, and I get 2 squared plus 2. So you got a lot of 2's going on here. So this is one of those examples where it's going to take a little bit more algebra to solve. We can still solve for k. So we have 2 minus k equals, on the right side, we'll get 4 plus 2, so I'll get 6. Give myself some more space over here. If I go to solve this, I get negative k equals 4, so then k is going to be equal to negative 4 then, in this case. You might be wondering why on both of these two examples I didn't bother kind of dealing with the f of 2 or the f of 0 in the first example, and I could compute those. I just don't need to, since showing that the limit from the left and the limit from the right, since knowing that fact that those two limits have to be equal, since that was enough information to figure out what k is, although I could go find f of 2 in this example, I don't really need to because I already solved what the question was asking for. Okay, our final example. I'm going to have you guys go ahead and pause the video and try example it on your own first, and then we'll check it together. Okay, example 8 says, find the value of k so that f of x is continuous everywhere. So again, I get to take that definition and I get to really use it now. So I know that the limit has to exist, meaning the left limit has to equal the right-hand limit, and I know that that equals the function value. So in example 8, our function says f of x equals 2k minus x if x is less than or equal to 1, and f of x equals x cubed plus k if x is greater than 1. So let's go ahead and start by computing the left and the right-hand limits. So we have the limit as x approaches, well, in this case, our breakpoint is at 1, so as x approaches 1 from the left of this function f of x, has to equal the limit as x approaches 1 from the right-hand side of f of x. Now as we approach in from the left-hand side, I want to use the value where I am less than 1, or in this case less than or equal to 1, so that will be the 2k minus x has to equal the limit as x approaches 1 from the right-hand side, so I'm using the value where I'm greater than 1, which is the x cubed plus k. Now this example is already a little different than the prior two because I actually have 2 places with the k, and we'll see if that means that I have to do extra work or if this is still enough to solve it. So let's go ahead and take both of these limits. So I can direct sub on both the left limit and the right limit. So on the left side I get 2k minus 1, and on the right side I get 1 cubed plus k. Well, simplifying that down, 1 cubed is just going to be 1 still. So I'm going to start to solve this and see if I can solve for k. If I combine like terms, I can subtract the k over, and I get k minus 1 equals, well, 1 cubed was 1. I can go ahead and add the 1 over, and I get that k is equal to 2. So although this function had k in both the less than 1 case and the bigger than 1 part of the piecewise function, still it was enough work for all that I had to do was show that since the limit from the left equals the limit from the right, compute each of those. Because they're equal to, I was able to solve for the value of k. That is the end of our continuity video, and this video has a lot of stuff jam-packed in it, from showing that a function's continuous, how do you justify and explain that, how do you justify and explain when a function is not continuous, what are all the different types of discontinuities, and not only what are they called, but what do their graphs look like? How do I prove that that's that type of discontinuity, and really explain that formally? We talked about one-sided continuities. What does that mean to be continuous from just the left or continuous from just the right? And then we have these kind of examples where we're working backwards. And if I know that the function's continuous, how can I work backwards to figure out, well, what was the original kind of equation equal to? What was that constant that we were solving for?